Thanks to the session chair for the introduction. I suppose there will be a session chair here. And today I'd like to talk about our latest work on synthesizing object state transformers for dynamic software updates. So let's first start with the problem of dynamic software updating and object transformation. Basically, dynamic software updates means patching a piece of system software on the fly without rebooting, both for the code and live heap data. You may expect this to be a difficult task because the runtime state of a system can be very fragile and have to be carefully managed. So let's first see how can we update code at runtime. Suppose that you have a piece of vulnerable code calling to an unchecked string copy, and you decided to fix it and patch it on the fly. Then you can load the safe upgraded code into the memory and patch a piece of trampoline code right at the first instruction of the vulnerable code. And this jump will hijack any control flow heading to the vulnerable function and redirect them to the safe one. Definitely, the real-world cases are not this simple. A compiler may inline the vulnerable function and distribute the call to the string copy everywhere, and you have to carefully find out every occurrence of them. Curious readers may refer to Michael Hicks and others' pioneering work on dynamic software updating. Even if we can lively upgrade code by inserting trampolines, dynamic update of data or objects in the heap brings more trouble. Suppose that you intended to change some data's internal representation from an array list to linked list. Since these two types of lists are of identical interfaces, this update doesn't change the program's semantics at all. However, immediately after live updating of code, the array list just becomes a trouble. The new version code operates on the linked list and is incompatible with all these stale objects. Therefore, dynamic software updating also requires to update the objects in the heap. This is done by a piece of object transformer code, which is a bridge between the old and new version objects. In this simple example, our object transformer iterates over all elements in the array list and inserts them back to the linked list counterpart. So the object transformer becomes our problem. Nobody has experience in writing object transformers. I speculate that many readers learn what is an object transformer for the very first time in this talk. But object transformers are indeed frequently required in dynamic software updating. Our study on 190 sample code changes in the full maintenance history of Tomcat 8 revealed that even though most class changes can be dynamically upgraded, there are still considerably amount of class changes that require their transformer. So this paper's problem became, can we get the object transformers automatically for free? So given old and new version test cases, conceptually one can enumerate all syntactically valid programs until a test passing transformer is found, or this is known as the syntax-guided synthesis. However, this does not scale to large projects like Tomcat. The patch looks complicated, and I'm not going to explain this case in detail. Rather, I'll try to illustrate how our algorithm found an object transformer by reassembling the existing source code. We observed that object transformation is a quite different scope than the existing program synthesis work, like programming by examples, like the famous flash fill functionality in Microsoft Excel. In existing program synthesis, an important goal is towards generalizability towards previously unseen tasks. Object transformer synthesis, on the other hand, can be regarded as another extreme. Transformers can be made by best reusing existing source code logic. Therefore, in this paper, instead of designing a domain-specific language for describing object transformer, we first tear down the source code into pieces called small gadgets, which are statement-level code snippets for later reuse. Specifically, for each statement, we leave variables as typed holes such that we can fill in something else later. Since a statement usually reflects an atomic piece of application logic, even a single gadget may carry a lot of semantics for object transformation. Like the first gadget in the figure, which reads as the socket's I/O channel's key for the polar selector. Such a piece of long logic may be very much useful in object transformation. With these gadgets, our domain-specific language for object transformer synthesis is then designed around gluing the gadgets with minimal complexity. The domain-specific language has simplest if and while statements, in which conditions can only be gadgets, negations, or null checks. Everything else are copy-pasted from project source code. There is also no arithmetic, Boolean, or logical operation at all. We argue that whenever these kind of operations are needed, they can be found in the source code. We search for the object transformers by a standard syntax-guided search. Given old and new version objects, we try gadget applications by filling the holes with available values or emitting an open if or while statement. Each time we found an object transformer, it will be sent to the test case. With the expressiveness of gadgets, we enclose quite a long logic in this object transformer for the motivating example. This transformer exploits an implicit one-one object correspondence invariant of Tomcat, even without knowing it. And such a transformer will be very difficult to synthesize from scratch. Even with a domain-specific language of minimal complexity, the search space is still huge because there can be millions of gadgets. To boost the search, we gave shorter and structurally simpler code with a higher score. Our algorithm can only handle maximal expansion of 10 steps, and the algorithm also does not consider nested loops. This echoes our belief that nearly everything needed by an object transformer can be stolen from the source code. To better steal the source code, our search algorithm also favors natural programs that look like a blend of a few streams of existing data flows in the source code. If we observe that statements 1, 2, 3 are data dependent in the source code, it would be better to use them as is in the order of 1, 2, 3, but not in the reverse order 3, 2, 1. Please refer to our paper for the technical details. For the experiments, we applied our algorithm to a set of 26 field updates sampled uniform at random in Apache Tomcat and Apache FTP server. The synthesizer is a given time limit of 30 minutes. For all cases that our algorithm can provide a transformer, there are top 1 hits. But this is not because we are always generating the correct transformers. This is partly due to the sufficiently strong test cases. For example, the search will always return a simpler and mostly correct transformer without null check before it attempts to guard the access with a null check. This can be potentially improved by incorporating program synthesis tricks like angelic conditions. The overall results are significantly better compared with the state-of-the-art. Our previous work, Altis, is a fancy black box approach based on synthesizing a method invocation history on the old version object and replace the history for the object transformation. Generating an inverse for complicated method is a bit too much for Altis. TOS, on the other hand, synthesizes everything from scratch based on the fundamental observation that every object eventually breaks down to primitive types and arrays. This is not a practical approach for the complex updates. There are a few interesting object transformers to share with you. First, our algorithm found an even simpler object transformer for the motivating example. It's just a one-liner of calling socket.getAttachmentForce, which overuses the getAttachment API. Even us did not identify such a possibility in our empirical study. The second case is a loop with nested conditions. In our domain-specific language, it consists of a constructor called a while loop, an if condition, an array access, and 2 method invocations. Without the idea of stealing control flow from source code, synthesizing this transformer would not be possible. Finally, for the conclusion, in this talk, we briefly overviewed the problem of dynamic software updating and analyzed the challenge of object transformer synthesis. The basic idea of this paper is to crush the source code into smaller reusable code snippets, they're called gadgets, and reassemble them to get an object transformer. For the takeaways, this paper demonstrates that program synthesis by code reuse beyond the component-based synthesis of a series of API calls can be made possible. We're going away in the anti-direction of program synthesis with no need for generalization. Can this idea be applied to other synthesis tasks like program repair? We still have a long way to go. Furthermore, this paper also showed that dynamic software updating for server programs under long-term maintenance upgrades may be possible. Generally, the code changes for maintenance upgrades are evolutionary, but not revolutionary. And this is the foundation of the validity of dynamic software updating. And finally, I'd like to thank all collaborators on this work. And I guess here is the time for questions and answers.
Hello, back to live space for question and answer. And I hope you enjoyed the video. It was a really nice presentation. And I am here with the 2 first authors of the paper, Zelin Zhao and Wan Yang, for answering a question that you can pose in the chat. As I write down in the chat, this work won the Distinguished Paper Award of the IXI traditional ACM SIGSOFT Award, and also was the only one that was given the ACM European Council Best Paper. So was really well received by the program committee, and I think it's a very interesting piece of work. So while people that maybe is a bit shy in writing down warm up, I have just one question. So I was a bit confused by this thing that you say that you take an object, you disintegrate it into little fragments, and then you can again put them together and reassemble again, obtaining an object. So maybe I missed this, but how do you, which is the strategy that you use to assemble again this code fragment? Do you have some heuristic, or you make any possible combination and then test? What do you do?
Yes, thanks for the very nice question. Here's the clarification. We first cut the program into a lot of pieces, and then we just try every possible combination of the possibility of assembling them together, from the simplest one to the hardest one, and ranked by some ranking functions, which can be referred to our details in the paper. And this is also something called program synthesis or syntax-guided synthesis. We have proposed a domain-specific language, and like the glue between the gadgets or the small code snippets, statements from the code. And we glue that little fragments by a domain-specific language. And we simply enumerate all possibilities. So it's a huge search space. And one of the major contributions in this paper is, I guess, which section? I guess it's in section, a lot of formulas. It's about the technical contributions for pruning the search space to make it practical. Yeah, I guess. So just a very brief clarification. Many technical details, please go to the paper. It's a little bit difficult.
Yes, yes. And I don't want to take all the space. I would have even more questions, but I would like not to take all the space from the audience. So
audience can join this video, right?
No, they can only write in the chat, but they should be now practical and know that they can meet you in the discussion room. After that, this time terminates, there is a pop-up that come out for the discussion room, and there people can ask you question with the camera on and their microphone. But not here.
Also,
we are the only.
I tried the answer, right?
Yeah.
Awesome.
Yes, yes. So, Zelling and Yuan, while we wait for more questions, how do you understand that one of the patch of the update that you made is valid?
Also,
you have a validation phase. You have a validation phase of the update. How do you understand that it is valid, or you reject it because not valid?
We have test cases. We write strong test cases to validate each generated program.
Yeah, so the difficulty is which test cases, random or?
We wrote the manual test cases to for sure that important branches are covered. Yeah.
Ah, okay. So this could be something to improve maybe in next work, because manual could be, yeah.
We reuse some test cases from the Tomcat test suite. And if we don't feel that's enough, we add some more to filter them out. And eventually, they give us, the test cases gave us quite good results. That every top one hit is the one we wanted. That's something really amazing. Partly because we wrote very strong test cases. Yeah. And we don't have any better idea of how we can say automate this process, I guess. It's maybe out of this paper's scope. Yeah.
Yes, maybe for future work.
Yeah. In the future, actually, we have planned maybe for the future work, we want to let developers to write some gadgets, because it's our framework is not picky about what kind of small code fragments. Now it's a fully automatic process, so everything is extracted from the program. But in the future, I guess we can let the developers to provide some useful hint manually, just a few hints, and perhaps we can get the rest cases which we cannot solve in this paper. I guess we solved about 60%. Yeah, in the sample, the random sample, the updates, and the rest is perhaps solved by the manual. We are trying to get this number to 100%.
Nice, very interesting. And I was not knowledgeable of this dynamic software update trend, so my fault. And so it was an occasion also to go and learn about this research path. Very interesting.
It's a little bit technically difficult, right? Patching something. Yes, if there is no question, I can just say a little bit more about dynamic software updating, right?
Yes, please.
So you can say if you want to patch just a piece of code, like a C program compiled down into the assembly and the machine code. You can replace the function. You changed. Just patch a jump instruction, jump to the updated code, and then the code gets updated. So generally, updating code is to readily solve the problem. If you do not consider the compiler tricks like inlining, which I mentioned in the paper, you can refer to the case splice paper, very nice piece of system paper to really solve the C case. But for the Java case, like if we change the data structure from the linked list to array list, or something in the real, like the motivating example in our paper, for more sophisticated object transformations, we have to update the heap state to get a successful dynamic software update. So this is really the challenge was, and this is what really we found that existing work fall short down. Yeah, I guess so. This is the motivation of our work.
Interesting. Okay. So congratulations again. No, we still have more than 1 minute to go if people will write question, but maybe not. So in any case, keep up the good work, and maybe see you in XC 2022 with 85% of success.
I guess there won't be an XC submission, but I guess we have some other synthesis work to submit on XC 2012 if 2022. Yeah, 22. I guess synthesizing some Android apps for your smartwatches. I guess we're doing this work. Yeah.
Okay.
Some fancy synthesis work. Yeah. Wish us good luck.
Yes. Good luck and congratulations.
Yes, thanks.
I don't want to cut while I am talking, so maybe I greet now, and thank you again.
Yeah, awesome. And, thanks, everyone. Thanks for listening to our talk. Yeah.
Thank you.
Thank you.
Very nice. Okay.
Bye.
Bye.
没事的，他们现在不问，一会儿应该也不太。